Hey folks, welcome back. We are getting ready for our dynamics exam, doing some review problems. In this problem, we are looking at impulse and momentum, and here's the physical system. We have an incoming bullet at A. We're given that it is 25 grams, so 0.025 kilograms. It is traveling along the horizontal at 600 meters per second. It ricochets off of the plate and drags for 10 millimeters and then leaves at this trajectory from C to D, which is 20 degrees from the plate surface. We are given that between B and C, the average velocity is 500 meters per second, and as it leaves, the exit velocity is 400 meters per second. In this problem, we are asked to find the magnitude and direction of the impulse force. So, to begin with, let's draw a diagram of the impulse force, right? So momentum and impulse diagram, which we will have to do on our exam. So let's see, we can represent the plate as a single bar, right? So we have a bullet coming in, make a little bullet here. Okay, this is mv1, and then we're going to have our impulse force, like this. Let's put a little geometry on this guy here. We'll say that this is 15 degrees. Okay, this is also 15 degrees, and we'll fill this in a second. I like to work, when I do these, it often makes sense to do the impulse part last, because the whole point of the exercise is to help to answer some questions about the impulse forces themselves. Okay, so this is leaving, the angle here is 20 degrees. This is V2, I guess it's MV2. Let me put that over here so it's a little bit easier to see. So MV2. Okay, we're still at 15 degrees here. And we need to figure out what our impulse is. Well, impulse, force times direction, we know that. I can clean that up a little bit, right? There we go. Okay, so let's define an axis. First, let's put our little bullet in here. And this time, we'll put it there, right? It's dragging along. Let's define this as the tangential direction, and this as the normal direction. And that will allow us to solve it much more easily. So, we need to know which direction the normal force and the tangential force is in this system. Well, the bullet slows down as it slides along, right? It goes from 600 to 500 to 400. So we know in the that the tangential component, at least, is negative, right? So this will be F tangential times some delta t, right? We also know that the plate deflects the bullet upward, right? So the only way that can happen is if the normal force is in the normal direction. And again, this is times delta t. Okay, so we need to solve for these forces, Ft and Fn. So in general, let's draw a line here to make things a little bit easier to see. So impulse in general is not u, it's I. So let's see, F delta t is equal to m times v2 minus v1, right? And if we divide out delta t on both sides, then we get m over delta t. Okay, well, let's see. We can do the velocities, but we don't yet have delta t, so let's find that. Delta t starts with the velocity. So velocity is dx over dt, so let's just say x over delta t. So that gives us that delta t is equal to x over v. Well, our x is 10 millimeters, so that is 0.01 meters. Our velocity is the velocity while it's sliding along here, and we're given that that is an average of 500 meters per second. And when we run this through the calculator, we get that this is 2, and I use E, so it's 2 times 10 to the negative 5 seconds. I use E because it's more compact, and then I don't have to pay attention to superscripts. So that's our delta t. So let's see. Let's go in the normal direction. Do that first. What do we have? We have, oh, hold on, we got to drop, if we divide that, then we have to take it out, right? So we have f in the normal direction is equal to m over delta t. M is 0.025. Delta t is 2 times 10 to the negative 5. Okay, and that is going to be v2 minus v1. So in the normal direction, v2 is 400 times the sine of 20 degrees, and that's going to be minus v1. Well, v1 is coming in, and it's coming in negative to the normal direction, right? So it's going to be plus 600 times the sine of 15, right? And that gives us that if n is, let's run this through the calculator, so 0.025 divided by 2e negative 5, and that's going to be times 400 times the sine of 20 plus 600 times the sine of 15. Okay, and I'm going to divide this by 1,000 because I already know that I'm going to get a huge number. And that gives me 365.124 newtons. Wait, not newtons, kilonewtons. Right, because I divided by 1,000. So that's one of them. All right, now we need in the t direction. Right? Okay, so same thing. F sub t is equal to 0.025 over 2 times 10 to the negative 5 times v2. Let's see, v2 is 400, not sine this time, it's cosine. Cosine of 20 degrees minus, and this time the what do we got? We got 600 cosine of 15 degrees. Okay, so when we run this through the calculator, let's see what we get. 0.025 divided by delta t times 400 cosine 20 minus 600 cosine 15 and that gives us minus 254.6 kilonewtons. Okay, and does that make sense? Well, let's see. It's in the negative direction, so yeah, it makes sense. Okay, sweet. So we need the magnitude and direction. All right, well, magnitude is easy. That is the square root of f in the normal direction squared plus f in the tangential direction squared. And let's calculate that. So 254.6 squared plus 365.124 squared gives us F is equal to 445.1 kilonewtons. Okay, that's one. Now we need the angle. Well, let's see. The angle, we have the components, right? So rise over run. Let's call this theta. So that's going to be the inverse tangent of rise over run. So the rise is 365.1. Go ahead and add the 24 there. The run is minus 254.6. Okay, so that gives us theta is equal to, let's see, inverse tangent 365.124 divided by minus 254.6, and that gives us minus 55.112. So that is, let's see, that is pointing down, but we're interested in this. So this is the inverse tan does that, right? So sometimes it'll give you a negative number. So what we do is we add a 180 to that because we're interested in this angle, right? So let's see, 180 plus that, is that right? Yeah, okay, so this is 124 point, we can just say 9. Right, so that's 124.9, and what this is that it is this direction here, so it is going this way, and so what we're interested in this reporting is to report it in the same direction that it was originally in. So what we'll do is we'll add 15 degrees to that, right? So theta is going to be equal to 15, so 139.9, and here I'm going to go ahead and use the directional notation just so that it's really clear what we're looking at, and I'll just say that's the x direction there, and that way whoever's reading this knows that it's reported from the direction of the horizontal, right? So typical angle reporting protocols. Anyway, there you have it. I hope that was helpful, and I will see you in the next video.